capital D equals 1 by h times delta minus 1 by 2 delta square plus 1 by 3 delta cube minus etc., where capital D is the differential operator, h is the interval of differencing, and delta is the forward difference operator. Also, hd equals log of 1 plus delta. Also, it equals minus log of 1 minus del, which is the backward difference operator del, and hd equals sin h inverse mu delta, where sin h inverse denotes the inverse hyperbolic sign. Let's look at the proof. By Taylor's theorem, we have f of x plus h equals f of x plus h by 1 factorial f dash of x plus h square by 2 factorial f double dash of x plus etc. Since d is the differential operator, we have f dash of x equals d applied on f of x, f double dash of x equals d square applied on f of x, and so on. Thus, f of x plus h can also be written in this way. Here, f of x is the common input to every term. Thus, we have 1 plus hd the whole square by 2 factorial plus hd the whole cube by 3 factorial plus etc. is the operator which acts on common input f of x. We have e raised to x has the expansion 1 plus x square by 2 factorial plus x cube by 3 factorial plus etc. Replacing x by hd, we have e raised to hd equals 1 plus hd the whole square by 2 factorial plus hd the whole cube by 3 factorial plus etc. Thus, this square bracket can be replaced by the operator e raised to hd. We have when shift operator e acts on input f of x, the output displayed is f of x plus h. We have proved here that f of x plus h equals e raised to hd applied on f of x. From these two deductions, we have shift operator can be equated to the operator e raised to hd. Relation between shift operator and forward difference operator is given by capital E equals 1 plus delta. Since we have proved capital E equals e raised to hd, we have e raised to hd equals 1 plus delta. When you take log on both sides, you get hd equals log of 1 plus delta. Since log of 1 plus x has the expansion x minus x square by 2 plus x cube by 3 minus etc., we have log of 1 plus delta can be expanded as delta minus delta square by 2 plus delta cube by 3 minus etc. When you multiply both sides of this equation using 1 by h, you get d equals 1 by h multiplied to delta minus delta square by 2 plus delta cube by 3 minus etc. Hence, we have proved the relation differential operator d equals 1 by h times delta minus delta square by 2 plus delta cube by 3 minus etc., where delta is the forward difference operator. We have here proved hd equals log of 1 plus delta. It remains to prove hd equals minus log of 1 minus del and the relation sin h inverse mu delta equals hd. Since we have backward difference operator equals 1 minus inverse shift operator, we have inverse shift operator equals 1 minus del. Since capital E equals e raised to hd, we have e inverse equals e raised to negative hd, or we have e raised to negative hd equals 1 minus del from these two relations. Thus, when you apply log on both sides of this equation, you get minus hd equals log of 1 minus del, which can also be written as hd equals minus log of 1 minus del. Hence, this relation is proved. Now we will prove the relation sin h inverse mu delta equals hd, where mu is the averaging operator and delta is the central difference operator. Since we have hyperbolic sign, sin hx equals e raised to x minus e raised to negative x upon 2, we have sin h of hd equals e raised to hd minus e raised to negative hd upon 2. H, which appears inside the bracket, stands for interval of differencing, and sin h denotes the hyperbolic sign. We have e raised to hd can be replaced by capital E, which is the shift operator. E raised to negative 1 can be replaced by e raised to negative hd. Thus, we get sin h of hd equals e minus e inverse upon 2. We have e raised to 1 by 2 plus e raised to negative 1 by 2 multiplied to e raised to 1 by 2 minus e raised to negative 1 by 2 becomes e minus e inverse, because this is of the form a plus b into a minus b, which equals a square minus b square. When you evaluate a square minus b square, you get e minus e inverse in the numerator. Thus, we have sin h of hd equals this expression. We have Averaging operator mu equals e raised to 1 by 2 plus e raised to negative 1 by 2 upon 2. And central difference operator delta equals e raised to 1 by 2 minus e raised to negative 1 by 2. Thus, this expression can be replaced by mu multiplied to delta. Thus, we obtain sin h of hd equals mu delta, from where we get the conclusion sin h inverse of mu delta equals hd. In this relation, this h is the interval of differencing and sin h inverse denotes inverse hyperbolic sign.